Alright, we are going to look at recursive formulas here. So recursive formulas help us find a sequence, and a sequence is just an ordered list of numbers formed by some pattern. So you've been looking at sequences ever since you were in early elementary school. So for example, 2, 4, 6, 8, and so on. That is a sequence. So you've been looking at sequences for a long time. In Math 1, we go over recursive and explicit formulas, but I know I personally have not taught it that well the last couple years because it's a little bit tough for Math 1 students. So I want us to go back over this. What we're doing today would be the Math 1 version of this, and then tomorrow we're going to look at more complicated recursive formulas together in class. So a recursive formula is a formula that defines each term of a sequence using the preceding terms. So for example, in this really simple example I gave you, your rule each time is that you add 2 to the term before it, and that is going to give you the sequence that you have here. However, an explicit formula is a formula we can use to find the nth term of the sequence. So if I want to know the 7th term of the sequence, then I can have a formula where I just plug in 7 and it gives me the answer. So we'll look at some examples here so you can see the difference in these types of. Okay, so I want us to start from an explicit formula that is very much like what we've been looking at so far. So we've been doing exponentials, and so we know that this would be 10 times 2 to the x power here, which means we would have an initial value of 10, and then whatever we are dealing with here is doubling over every time period. So in this particular explicit formula, I would have, if I plugged in 0 here, I would get 10. And I'm going to fill in my table. Now, if I plug in 1, then that's going to be 10 times 2 to the first power, which is going to give me 20. If I plug in 2, I'll have 10 times 2 to the second power, so I'll do 2 to the second first, which will give me 4. 4 times 10 is 40, and of course you can use your calculator to plug these in as well when these numbers get larger. And then we'll have 10 times 2 to the third. 2 to the third power is 8. 8 times 10 is 80. And for 4, 2 to the fourth is 16, so I would get 160 right here. And then 2 to the fifth is 32, so I would get 320 here. So these are just the points that we would have on this graph for the exponential that we've looked at. Well, whenever we write a recursive formula, we are not wanting a formula where we can plug in the number of the term, but rather we want to look and see what happens from one term to the next term. So to get from 10 to 20, what could we do? To get from 20 to 40, what could we do? Now we could say here, to get from 10 to 20, we could add 10. However, if we look at the next term, if we add 10 more, we should get 30, which we don't. So adding 10 is not our rule that we're using here. Rather, to get from 10 to 20, I could multiply by 2. And then from 20 to 40, I could multiply by 2. And then from 40 to 80, I could multiply by 2. So each term that I have, I'm going to multiply by that term again. So for the recursive formula, I'm going to introduce some notation here. Typically for recursive formulas, we don't use our f of x and x notation. Rather than the x, we typically use an n. And rather than the f of x, we use a sub n. So n is the number of the term, and a sub n is the result you get from that. A recursive formula is going to rely on a sub n and typically a sub n minus 1, although it could be a sub n plus 1 as well. So for a recursive formula, what we're going to do is we're going to say a sub n equals, and a sub n is our term that we have over here, and we are going to say to get to the next term, you have to take 2 and multiply it by a sub n minus 1. So if a sub n is a term, then a sub n minus 1 is the term that comes before it, because it would be preceding if you subtract 1 from it. So if this is a sub 2, then a sub 1 is the one that comes before it. You can kind of think of this, sometimes whenever we teach this in Math 1, we call this the next term, and then what you have now, so you can kind of think of that. So if you take what you've got now and you multiply it by 2, it'll give you the next term. A lot of times with the recursive formulas, we will also state a beginning term, so a sub 0 would be 10 in this case right here. Sometimes, depending on how you're given recursive formulas, sometimes you'll state a sub 0. Sometimes you'll give a sub 1. It really doesn't matter which one you give. IXL is going to use the a sub 1 a lot more. I typically like the a sub 0 a little bit better because a sub 0 is your initial value, and then you have this number here is the one that you're multiplying and raising to that power. So these types of formulas, these exponential formulas, also have a special name when we're talking about sequences. So this type of sequence is called a geometric sequence. It is a sequence in which each term is found by multiplying the previous term by a fixed number, hold on, let's scroll down here, called the common ratio. And this is something you sometimes see on the ACT. I don't know if you guys will even take it this year with all of this going on, but geometric sequences, sometimes they'll ask if a sequence is geometric, or we'll look at the other types soon. And if you can find the next number in the sequence by multiplying, then it is a geometric sequence that you're dealing with, which means it's going to look exponential if you graph it. Okay, here's another type of formula that we are very familiar with, although I have went ahead and used the a sub n and the n right here. But remember, on our last problem, this was like the x, and this was like the f of x. So this is like saying f of x equals 2x plus 5. So this should be a type of function that's really familiar to you. This is a linear function. So if we want to know a sub 0, we would just plug in 0 for the n right here. So 2 times 0 plus 5 would give us 5. And then if we plugged in 1, 2 times 1 plus 5 would give us 7. 2 times 2 plus 5 would give us 9. 2 times 3 plus 5 would be 6 plus 5, which would be 11. 2 times 4 plus 5 would be 13. And 2 times 5 plus 5 would be 15. So you can see here the table that we would end up for this. This is a linear function. Now, when we're looking at recursive formulas, we're looking at what happens from one term to the next. So we're not looking at what number of the term we're dealing with. We're looking from one term to the next. So from 5 to 7, I could add 2. And then from 7 to 9, I could add 2 again, and so on. That's the pattern that we have for this formula. So, for our recursive formula, we could say a sub n equals, we're taking the term that we have right now, which we're going to call a sub n minus 1, and to get the next term, we have to add 2. And then a lot of times we'll include a sub 0 equals 5 here. Sometimes you might see a sub 1 equals 7. It just depends on what you're dealing with. I'm going to show you on IXL, you'll see a sub 1 a lot more. But You notice here that you're adding that slope of this linear equation, and then your y-intercept is your a sub 0 for this recursive formula. So whenever you have a linear graph, the recursive formula is going to look like this. These types of sequences also have a special name, and they are called an arithmetic sequence. It is a sequence in which each term is found by adding a fixed number called the common difference to the previous term. So if you have a linear graph, that represents an arithmetic sequence. If you have something that's exponential, that represents a geometric sequence. So let's look at some of the problems that we're going to see. Okay. First of all, I've just sort of shown you here, if you have a sub 1, that means the first term. If you have a sub 2, second term. A sub n is the nth term in that sequence. And then the term before the nth term would be a sub n minus 1. So if we're given this table right here, and we're asked to write a recursive, and explicit formulas for this particular table, then what we're looking at for the recursive is we're looking to get from a sub n, or a sub 0 to a sub 1, what do we have to do? And then to get from here to here, what do we have to do? And you can see we're going from -3 to 7, and then 7 to 17. So for these, I could add 10. Okay, so my recursive formula is going to be a sub n equals a sub n minus 1 plus 10. And then typically we'll also say a sub 0 equals -3. Okay, now if we think about writing an equation for this, then we are thinking about, or writing an explicit equation, then we are going to say a sub n equals, now we want this to be in terms of n. So if I want to know the 7th number in the sequence, I can just plug in 7. In this particular formula, you have to know the number that comes before it. So, like to find the next number, we would add 10, and then we would add 10 again, and then again, and again to find the 7th term. But for this, if I want to know the 7th term, I just want to be able to plug in 7. So, notice we're increasing by 10 every time we increase our n by 1. So the slope of this line would be 10. So we'd have 10n minus 3. So that amount that you're adding right here is your slope, and then the a sub 0 is your y-intercept. That's your minus 3. So that's what we would have for this one. And I think I've numbered my problems wrong because I've got 2 example 3s in a row here. So here I've got a recursive formula for 2, 3 over 2, 1, 1/2, and so on. So for this one, I'm not given a table, I'm just given a list. So to go from 2 to 3/2, I would have to add, or I'm sorry, not add, I would have to subtract 1/2. And then to get to 1, I would subtract 1/2 again. And then to get to 1/2, I would subtract 1/2 again. So I'm subtracting each time. Now, subtracting was not what we were talking about earlier, but subtracting is the same thing as adding -1/2. So this is an arithmetic formula. So we would say that our recursive formula is a sub n equals a sub n minus 1 minus 1/2, or you could write it as plus -1/2 if you want, but it looks better like this. And in this particular case, typically with these types of problems, they'll usually say a sub 1 equals 2. They usually call this a sub 1 right here. Sometimes maybe they'll call it a sub 0. It really just depends on who's writing the problem. A lot of times when they're asked for a recursive formula here, they won't ask for the a sub 1 or a sub 0. They just want this formula right here. Okay, so let's look at writing a recursive and explicit formula for the following table. So I'm going to fill this in here. So we're going to have 1, 2, 3, 4, 5, and we're going to have 125, 6.25. I'm just writing in the problem here. 1.5625 and 0.390625. Another room right there. All right, so this time we want to write recursive and explicit formulas. So I'm going to go from here to here. I'm thinking, what could I do to get from 100 to 25? I could subtract 75, but it's not going to work for the next problem. So instead, to go from 100 to 25, I could divide by 4. Or, the better way to think of this, because for recursive formulas, we really want to think about what we're multiplying by when we have something that's exponential. So instead of thinking about dividing by 4, I'm going to think about multiplying by 1/4. It's the same as dividing by 4. And then so I could multiply by 1/4 again, and I'd get 6.25. And I can multiply by 1/4 again, and I'd get 1.5625. So that's our formula that we have here. So for our recursive formula, we're going to have a sub n equals, we're taking whatever we have, like that 100 right there, that's our a sub n minus 1, and we're multiplying it by 1/4. Okay, so this would be our function that we're given. We would say a sub 1 equals 100 for this. Or, if we want to know a sub 0, because depending on the problem, you may want to know a sub 0, and I'm going to show you in a minute why you would want to know a sub 0. If I want to know a sub 0, I would need to go backwards in this list right here. So if I want to go backwards in this list, to get from 100 to 25, I had to divide by 4. So to get from 100 to the term that comes before it, I would have to multiply by 4. And so this would give me 400. And so a sub 0 would be 400. Now there's a reason I wanted to show you that. Because when you're writing an explicit formula for this, this is an exponential. And for an exponential, to know that original amount that you're starting with, that a value for your exponential, you really want to know a sub 0 right here. Because to write this formula, you would say a sub n equals 400 times 1/4 to the n power right here. So we would want to use that 400 instead of the 100 in this particular case. Now IXL does something a little bit different here. I'll show you in a minute, but this is what we would want to use. Let's move on. Okay, so for each of these, we're going to tell whether the recursive formula represents an arithmetic or geometric sequence, and then we're going to write an explicit formula that matches the recursive formula. So, if we have a sub n equals a sub n minus 1 plus 5, and a sub 0 equals -7, if you think about what's happening here in this formula, you've got -7, and then you would add 5 to get the next number, and add 5 to get the next number. In fact, I'm going to pull up Desmos over here. And let's just look at what happens. Let's add a table. And so I would begin with our a sub 0 term would be -7. And then I would have my first term, if I add 5, that'd give me negative 2. And then if I add 5 again, that'd give me 3. And then if I add 5 again, that'd give me 8. So I'm looking at this linear graph right here. And so since this is linear, if I want to write an equation for that, I'm thinking y equals mx plus b right here. Y equals mx plus b. But because we're using this recursive notation, instead of y, I'm going to use a sub n. So it's going to be m times n plus b. So instead of using x and y, you're using n and a sub n. So if I'm writing this formula, a sub n is going to equal, my slope of this graph is 5. I'm going up 5 over 1. So I'll have 5n plus b, which is my y-intercept, which is negative 7 right here. So this would be my explicit formula for this sequence right here. And for this sequence, you can see that that number that's added right there for this arithmetic sequence, that's my slope. And this a sub 0, that's my y-intercept. And I didn't write it down, but this is arithmetic, because we're adding each time. Okay, let's look at the next one here. This time we've got a sub n equals negative 2 times a sub n minus 1, and a sub 0 is 4. So we're doing negative 2 times a sub n minus 1. So since we're multiplying, this is going to be a geometric sequence. And let's make us a table for this one as well. So let me erase what we had over here. So our a sub 0, our initial term, is 4. And then to get the next term, we have to take negative 2 and multiply by the term that came before it. So negative 2 times 4 is going to give us negative 8. And then we'll have negative 2 times negative 8, which will give us 16. And then negative 2 times 16, which will give us negative 32. And then we'll have negative 32 times negative 2, which will give us 64. And then I'm going to keep going. We'll see. That'll be negative 128, I believe. All right, so let me zoom way out. This is going to be a crazy graph that we see because we're alternating positive and negative. And this is what happens to an exponential whenever the number that you're raising to a power is negative. So to write this as an exponential, we would write it this way. A sub n equals, our initial value right here is 4. So we have 4 times, and then the number you're multiplying by each time is negative 2 to the n power. So that a sub 0 is your a value out here, and that number that you're multiplying by, that is your b factor here, the growth or decay factor for this problem. All right, let's try a couple more of these. So here we've got a sub n equals 3 a sub n minus 1, and then a sub 1 equals 9. So this problem is going to be a little bit different than the last one because we're given a sub 1, not a sub 0. So let's just think about what this graph would look like. All right, I do not know a sub 0. I do know a sub 1, which is 9. And then to get the next number, I have to do 3 times 9. So 3 times 9 would give me 27. And then I've got to do 3 times 27, which is going to give me 81. And I'm going to multiply by 3 again, which is going to give me 243. And then if I multiply by 3 again, that gives me 729. And so I would really have to zoom out for this for you to be able to see all of those points. They're going to look like a line because they're so steep. I could change that there, but we can see this is exponential growth right here. So in order to be able to write this as an explicit formula, I really need to know what the a sub 0 is right here, because that is my initial value that I'm starting with. So I have to go backwards one step here. And so to go from 9 to 27, I multiplied by 3. To go backwards, I would need to divide by 3, and I would get 3 for that a sub 0 term. So the IXL is going to do this on pretty much all of the problems. It's going to give you a sub 1, so you have to go backwards to get the a sub 0 there. So our formula is going to be a sub n equals, our a sub 0 is 3 times 3 to the n power. So it'll be an exponential formula. So I did make a problem where I've got both numbers. So this 3 goes right here. Our a sub 0 goes right there. And then the 3 that we're multiplying by, that's the number that goes in the parentheses for our exponential. Okay, we've got one more like this to look at. So let's look at this one really quickly. In this case, again, we do not have the a sub 0. We've got the a sub 1. So this is going to be negative 1. Let me zoom back in. I think here's okay. And then so we are subtracting 6 each time. So negative 1 minus 6 would give us negative 7. And then negative 7 minus 6 would give us negative 13. And then negative 19. And that'll be enough for us to see the pattern here. So we can look at our points here. We can see we don't have our y-intercept. We need to know that a sub 0. So we were subtracting 6 to go in this direction. We would have to add 6 to get this value right here. So negative 1 plus 6 would give us 5 right there. And that shows us our line that we've got. So for this, we would have a sub n equals, and then our slope is negative 6, so we'd have negative 6n, and then our y-intercept is 5, so we'd have plus 5 here. So again, we had to find a sub 0, which was 5, in order to write that equation. And our a sub 0 is our y-intercept when we're talking about these arithmetic function or arithmetic sequences here, and our number that we're adding or subtracting, that is our common difference. That is the slope whenever we do this. So that sort of covers going from a recursive back to an explicit. Now let's look at explicit to recursive. So here I've got a sub n equals 4 times 3 to the n power. So we're looking at an exponential. Exponentials are going to be geometric. That means we're multiplying each time. So to write these equations, this part right here, your initial value, that is your a sub 0. And then this number right here, that 3, that's the number you're going to be multiplying by each time. So to write this equation, you'd say a sub n equals 3 times a sub n minus 1. That's your equation. You're multiplying by 3 each time to get to the next value. And then your a sub 0 would be 4. Now here's a good way to check to see if you've done this correctly. If you use Desmos here, our a sub 0 is 4. To get the next number, you would have to multiply by 3. So 4 times 3 is 12. And then 12 times 3 is 36. And then, that's probably good enough. We'll look at these here. So we've got these numbers. If we go down here and type in our formula, we're going to use x's and y's. Y equals 4 times 3 to the x power. Notice that that explicit formula goes right through all of our points right there. So we can feel confident that we did this correctly. So this would be our recursive formula for this geometric sequence. Okay, our next sequence, I'm going to go ahead and type in the equation, negative 5n plus 4, right here. And let's get rid of this stuff here. We are going to, oh, let's go back home. Okay, and so we can see our equation right here if we graph it. And so we want to write a recursive formula. So a sub n equals, and then we'll have our a sub 0. Our a sub 0 is that point right there where we cross the y-axis. It's our y-intercept here. It is going to be 4. So when you're talking about arithmetic sequences, that linear y-intercept right here, that is your a sub 0. And then what's happening whenever you have arithmetic sequences is we're starting at 4, and then each time we're going to subtract 5. So 4 minus 5 would give us negative 1. If we do negative 1 minus 5, that'd give us negative 6. And then negative 6 minus 5, minus 5 would give us negative 11. And you can see these are all lining up on our graph right here. So our rule is that we're subtracting 5 each time we go to the next term. So it would be a sub n minus 1 minus 5. So whatever the slope of that graph is right there, that is your common difference. That's the number you're adding or subtracting to your equation. So you're going to have several of these in iExcel. Your assignment that goes with this, I want you to do W6 and W7. However, for these, I do not want you to do these all day long, because iExcel sometimes can be so frustrating because it takes forever to get to a high score. So you only have to get a SMART score of 70 on these, because I do not want you to spend an hour and a half doing these problems. So if you spend more than 35-40 minutes on these problems, it is okay to quit. Let me know that you're having trouble, and we'll look at these on Tuesday. I just remembered one thing we need to look at in iExcel really quickly. So whenever you go to iExcel and you're going to go to that's Algebra 2. We're going to go to PreCal. PreCal, you guys will be doing W6 and W7. And I want to show you something on these here. Hold on. So one thing that you're going to see a little bit on iExcel is you're going to get some of these where a sub n equals negative 3, just negative 3. There's nothing else there. That means that you have a constant function. It's just a horizontal line, negative 3, all the time. So if that happens, every single term is negative 3. Negative 3, negative 3, negative 3, negative 3. So for these, what you're going to type in for these is just a sub n minus 1. So a sub n is the same as a sub n minus 1. So every term is the same. Every term is negative 3. And that will be what you get whenever you get those constant terms. That was on W7. On W6, you're going to see problems where you have the recursive and you're going to turn it into an explicit. Notice here, they give you a sub 1. So this is arithmetic. So negative 7 is your slope. So you're going to have negative 7 n. But this is not your a sub 0. So you've got negative 22. You had to subtract 7 to get each term, so you're going to have to add 7 to get back to a sub 0. So if you do negative 22 plus 7, you'll get negative 15. So that y-intercept would be negative 15 for that one. So be careful with these. Let's see if I can come across another one. So here you're adding 13 each time, so that's going to be 13n. That's your slope. But again, you've got negative 4 is a sub 1. You want to go backwards one more. So instead of adding 13, you'll have to subtract 13. So if you do negative 4 minus 13, you're going to get negative 17. So not 27. Negative 17 is going to be your y-intercept for that one. Now, here's one that I wanted to specifically show you for this. A sub 1 is negative 48. A sub n equals A sub n minus 1. That means A sub n is the same as A sub n minus 1. So if A sub 1 is negative 48, then the next problem, the next term, A sub 2, is also negative 48. And then the next one is negative 48. You just always have negative 48. So if you see one like this is just a constant function. It's a horizontal line. And so it's just going to be negative 48. No n's or anything, just negative 48. This is a constant that you'll have here. Now this one is exponential. So for exponential, remember it's y equals a times b to the x. Your b is this negative 4 right here, but remember you must go backwards 1 to get your a sub 0. So you're going to have to do, you're multiplying by negative 4 each time to get to the next term. So you've got to divide by negative 4 to get back to your a sub 0. So 8 divided by negative 4 is going to be negative 2. And then that'll be times negative 4 to the n power. Okay, here's one more. Let's do one more of those. So you've got negative 4 times a to the n minus 1, and you got negative 40 here. So your initial value is your a sub 0. You've got to go backwards 1. So negative 40 divided by negative 4 is going to give you 10. So you're going to have 10 times, and then this number you're multiplying by here is your negative 4, and it'll be to the n power.
Can I show him how to write my name?